Hello all! Recently a bunch of math YouTubers have created videos about their favorite numbers greater than 1 million. They've also invited the public to create videos doing the same, choosing one number greater than 1 million and talking about it. So that's what I'm going to do today. My number is 1,114,112. So what's so special about this number? Well, we could start by looking at its prime factorization. It's 16 2's, but then there's this extra 17, and that's fine, but not particularly special. But actually, the reason I chose this number is not for its mathematical properties. The fact that we have 2 raised to the power of a power of 2 is suggestive that this is a number relevant to computers, since computers often chunk bits into groups that are powers of 2 in size. In this case, 1,114,112 is the number of possible Unicode code points. So let's back up and talk about Unicode. Computers can store a lot of different kinds of information, but on the actual hardware, everything is ultimately stored as integers, or well, technically as bits, but we'll get back to that in a moment. If your information is not an integer, like a video file or an image file, you'll have to do some sort of conversion between these bits and the kind of information you want. And one very important kind of information is just plain old text. Unicode is a standard that converts between text characters and numbers. In principle, Unicode simply assigns a number to every character that we ever want to represent. So the capital letter A is 65, the lowercase letter a is 97, the lowercase e with an acute accent is 233, the Arabic character Shin is 1588, the Chinese character Gao is 39,640, the guide dog emoji is 129,454, etc. I say this is in principle all they do, but language is complicated and messy, so they also have to deal with a whole host of issues to be aware of when dealing with text. For example, how to handle right to left or top to bottom text, like Hebrew and traditional Mongolian. How to handle cases where the appearance of the character depends on the surrounding characters, like in Arabic. Deciding whether or not the traditional Chinese, simplified Chinese, and Japanese variants of a Han character count as the same character or not. And how to handle characters that are not actually characters, but instead just modify surrounding characters. And side note, this is why the official term is code point rather than character, to include these characters that are not actually characters. This isn't relevant to the number 1,114,112 at all, but I thought it was interesting enough to mention. But yes, back to 1,114,112. So far, it sounds like we could keep assigning more and more code points to higher and higher integers. Why is there a limit at all? It comes back to the difference between integers and actual bits on the computer, which I brushed aside earlier. On computers, bits are chunked into bits of 8 called bytes. A single byte can only represent 256 different characters, which is barely enough for the Latin alphabet and common diacritics, let alone any other scripts. But 2 bytes can represent 65,536 different characters. This was more than the number of code points defined at the time in the Unicode standard, so that was that. Every character was 2 bytes, easy, done. But then more and more scripts and characters and code points were added, and it became clear that more than 65,536 characters would be needed. So they came up with a clever scheme called UTF-16. Code points smaller than 65,536 would be represented with 2 bytes, just as before, so old text stored in this manner could still be read under the new UTF-16 system. Code points larger than 65,536 would be represented instead with 2 sets of 2 bytes, called a surrogate pair. In theory, we could represent just over 4 billion different code points in 4 bytes. But if the computer comes across 4 bytes, how does it know if it's 2 characters less than 65,536 or 1 character more than 65,536? Well, it was decided that the first surrogate of a surrogate pair would always start with the bits 110110, and the second surrogate of a surrogate pair would start with 110111. 2 bytes that don't start with either 110110 or 110111 would be treated as a single character. So that leaves 20 bits for actually encoding information. That's 2 to the 20 different available code points greater than 65,536, or 1,048,576. Add that to the 65,536 of our original code points and we get out, indeed, 1,114,112. But this does lead to one final question. What happens to the code points between 55,296 and 57,343, which are less than 65,536, but would start with 110110 or 110111 in binary? Well, when UTF-16 was created, these code points were not in use, and the Unicode Consortium decided it would never assign these code points to any characters to preserve compatibility with UTF-16. So I guess you could argue that these are technically not available code points for Unicode characters. So maybe my mega favorite number should be 2048 less. And furthermore, Unicode has also predetermined several other ranges that they will never assign code points to, called the private use characters, intended as extra code points that you can use if you need to make your own custom characters that aren't defined by the standard. There are 137,468 such private use characters, so maybe we should subtract off again 137,468. And there are also 66 more code points that they just declared as so-called non-characters, which are not intended even for private use, though it is technically not invalid to do so. So subtract off 66 more? After all this would give a true total of 974,530 possible Unicode code points. But that's less than the required 1 million, not to mention arising only from so many messy details and caveats. So I'll stick with the simple 1,114,112 and say that's my hashtag megafave number. In the description, I'll link to the playlist of all the megafave number videos. The information presented in this video is accurate to my knowledge, but any errata or clarifications will be in the pinned comment or in the description.